In this video, we're going to look at the proof of the fact that the sum as k goes from 1 to n of k squared is given by n times n plus 1 times 2n plus 1, all divided by 6. I actually want to look at the proof given in our textbook by the authors because this is a good example of learning how to read an advanced mathematics textbook by doing what I call active reading. That means having a pencil and paper in your hand while you are reading. And so I'm going to be modeling that kind of an exercise in this particular video. The proof given in our textbook looks like this, and I encourage you to stop the video and read it for just a second, but we are going to read it together in pieces. So hopefully you've done that. The thing that I want to note is that the authors have set this up as an example with a solution. And so the solution is actually the proof. And the thing that we want to prove is that the sum of the first n squared, the sum of the first imperfect squares is given by this formula. And of course the authors ask, why does the formula hold? The first statement they say is to let Sn denote the expression on the right side above. That means Sn is this mess, not this mess. And I want to get that written down on a sheet of paper so that I do not forget it. So S of n is equal to n times n plus 1 times 2n plus 1, all divided by 6. Now, the next thing the authors say is clearly S of 1 is equal to 1, and so the formula works for n is equal to 1. As a mathematician, this tells me that the proof is really based on something called the principle of mathematical induction. If you are a math major, you will study mathematical induction in a course that at Buff State is called Math 270, Discrete Mathematics. For those of you who aren't math majors, we'll get just enough of a flavor of mathematical induction to see why this is working in this particular problem. But I want to verify this fact, and I want to see what the authors mean by that. So I come over here and I actually compute S of 1. That's simply a matter of plugging in n is equal to 1 into this expression. So S of 1 is going to be 1 times 1 plus 1 times 2 times 1 plus 1, all over 6. And when we sort that through, S of 1 is going to be 1 times 2 times 3, all over 6. Yeah, S1 is equal to 1. So I'm going to check that fact off. And when they say that the formula works for n is equal to 1, they mean that we have an equality right here. So I want to verify that the formula works. So if I look at the sum as k goes from 1 to 1 of k squared, that is also 1, and these two things are equal. And that's what they mean by the formula works for n is equal to 1. That if I look at this expression and I look at this expression and I plug in n is equal to 1, I get the same thing. Now the next step would formally be called an induction step, but since the authors are not trying to teach mathematical induction, but rather give you an insight into why this formula works, they simply say this step here. Now consider now consider S of n minus S of n minus 1. If the formula of Sn is correct, we should have this mess will simplify to n squared. And then they say, by definition, this mess is equal to this. And then there's some stuff here that ends with, and it does reduce to n squared. In other words, the authors are claiming that if we start here, this mess will be n squared, and they're saying that the formula will work because of this fact. In other words, I want to state the logic of this area of their proof very carefully. So the actual logic that the authors are using is this. If the formula is wrong, and let me clean up my handwriting there. So the authors are really making the argument that if the formula is wrong, then s of n minus s of n minus 1 won't simplify to n squared, but Sn minus Sn minus 1 does equal to n squared, so the formula is correct. And it's important to understand that that's the logic behind the argument. The authors are not saying, since the formula is right, this will simplify. They're really saying, since Sn minus Sn minus 1 simplifies to the right thing, the formula is correct. Now, I also want to think about what else the authors are doing here. So we're going to start here. We want to show that, but the authors say some basic but careful algebra, and then they tell you what it is, shows that this side does indeed reduce to n squared, and then because of the fact that the base step is true, everything works out. Well, there's a lot of algebra that the authors are hiding, and when the authors say something like, basic algebra shows, that's another invitation that you need to get your pencil and paper out and do the algebra. So I want to do that on my next panel. So let's see. Sn is given by the expression n times n plus 1 times 2n plus 1 all over 6. Sn minus 1 then is going to be, I'm going to plug in n minus 1 for each one of these n's, and when I do that, I'm going to get n minus 1 times n minus 1 plus 1 times 2 times n minus 1 plus 1. And all of that is divided by 6. So Sn minus 1 is going to be n minus 1 times, well, let's see, n minus 1 plus 1, that's just a fancy name for n. And then when I do this piece of algebra, I'm going to have 2n minus 2 plus a 1, and I still have all of this stuff divided by 6. And I can clean this up to read n minus 1 times n times, and this expression here is going to simplify to 2n minus 1. And just to go back and check, that is indeed what the authors have put in right here for Sn minus 1. That is Sn minus 1 in the author's proof. Now the authors are saying that if my formula is correct, I should get n squared. So if my formula is not correct, I shouldn't get n squared. So now what I've got to do is do this particular piece of algebraic simplification. In other words, I want to look at Sn minus 1. So let's now look at Sn minus 1 now looks like n times n minus 1, no, n times n, let's see, I've got to go back and check Sn, n plus 1. So Sn is n times n plus 1, ooh, my handwriting's letting me down, let's just start over. Sn minus 1 is going to be n times n plus 1 times 2n plus 1 all over 6 minus the expression that we just got done computing up there, which is n minus 1 times n times 2n minus 1 all over 6. Now, a lot of students, when they're being asked to simplify this kind of algebra, start out by trying to multiply everything out, and things can get pretty bad pretty fast. So what I want to do is I want to actually do the algebraic simplification in a way that may not immediately strike you as being the first thing to do, but I want you to start looking for these tricks. I have an in there, and I have an in here, and I have a 6 here, and I have a 6 here. That means I can factor an n over 6 out, and that's going to reduce the number of things that I have to multiply. So what's left in the first term is I've got an n plus 1 times a 2n plus 1. And what's left in the second term is I have an n minus 1 times a 2n minus 1. And I don't have a denominator because the denominator got factored out. Now I'm all set to do the multiplications. For this multiplication here, I'm going to get n squared, and then I'm going to have 2n plus one more n, we're going to have 3n, and then I've got a plus 1 at the end. And now I need to have this minus sign multiply everything, so I'm going to leave that minus sign out. And I get n times, I made a mistake here. This is n times 2n, that's a 2n squared. And so we're going to have n times 2n, we have a 2n squared here. And then we've got minus 2n minus 1 more n. That's going to be a minus 3n. And then we have a negative 1 times a negative 1. That's going to be a plus 1. And there's my ending parentheses. Now I've got n over 6 times. And now I'm going to distribute this minus sign out over all three of those terms. So we have 2n squared plus 3n plus 1 minus 2n squared minus a minus 3n minus a 1. And notice the 2n squared and the minus 2n squared cancel each other out because they add to 0. We have a plus 1 and a minus 1, and they add together to be a 0. So what I'm left with is n over 6 times 3n plus 3n, and that is n over 6 times 6n, and let me clean up my notation. And that 6 divides out, and we are left with n squared. And so the formula works for all of our values of n, and that completes the author's proof.